Hello. In this presentation, we'd like to share our recent work entitled ϕ-DPO, Fairness Direct Preference Optimization Approach to Continual Learning in Large Multimodal Models. This research is a collaboration between the University of Arkansas and the Carnegie Mellon University and is supported by NSF. Large Multimodal Models, or LMMs, have recently shown impressive performance across many vision and language tasks. However, in real-world deployment, these models must continuously adapt to new knowledge, new tasks, and changing data distributions. Retraining an entire large model every time new information arrives is extremely expensive, while directly fine-tuning on new data often causes catastrophic forgetting, where the model loses previously learned capabilities. To address this, continual learning has become an important direction for LMMs. However, existing approaches still face major challenges. Methods such as LoRa often struggle under imbalanced multimodal data and can still suffer from severe forgetting over time. Meanwhile, even vanilla direct preference optimization, or DPO, remains highly sensitive to skewed data distributions. This problem becomes even more significant in continual learning benchmarks, where tasks arrive sequentially and naturally create topic imbalance across time. To overcome these limitations, we propose ϕ-DPO, a fairness-aware continual learning framework for LMMs. Our approach is designed to reduce catastrophic forgetting, continuously adapt to new tasks, and remain robust under imbalanced multimodal data distributions. Our contributions are as follows. We propose ϕ-DPO, a fairness-aware DPO framework for continual learning in large multimodal models. Our method reduces catastrophic forgetting while adapting to new tasks over time. We introduce a new fairness loss to handle imbalanced multimodal data distributions and provide theoretical analysis and benchmark preference labels to support DPO-based continual learning. Extensive experiments show state-of-the-art performance across multiple continual learning tasks. Unlike traditional continual learning methods, we reformulate continual learning in large multimodal models through reinforcement learning from human feedback. At learning step T, the optimization objective can be rewritten using a Lagrangian formulation, which naturally leads to a direct preference optimization, or DPO-based continual learning paradigm. The DPO objective plays an important role in stabilizing continual learning. Specifically, it prevents the policy from drifting too far away from the previous learning step, helping mitigate catastrophic forgetting, while still allowing the model to learn new tasks. Next, we provide a theoretical analysis of the KL divergence term by introducing both a lower bound and an upper bound. The lower bound encourages the current policy, 𝝅t, to remain close to the previous policy, 𝝅t-1, reducing forgetting of previously learned knowledge. Meanwhile, the upper bound regularizes the optimization process and preserves adaptability to new learning tasks. However, under imbalanced multimodal data distributions, the gradient updates produced by vanilla DPO become biased toward dominant groups. In this case, the gradient difference between the observed distribution and the ideal distribution is no longer zero, meaning the optimization becomes unfair across different data groups. To address this issue, we introduce a new fair DPO loss with a focusing parameter, gamma. As supported by our theoretical analysis in Lemma 3, increasing gamma leads to fairer gradient updates and improves robustness under data imbalance. Here, we present the overall framework of our ϕ-DPO approach. The key idea is transforming our LHF-based continual learning into pairwise preference continual learning using DPO objectives. To support this setting, we also construct pairwise preference annotations for existing continual learning benchmarks. Previous benchmarks mainly provided instruction following data but lacked the preference labels required for DPO training. Our new annotations enable continual learning through preference optimization. Experimental results show ϕ-DPO consistently surpasses previous methods on both the MLLMCL and COIN benchmarks. It scores 85.58% on remote sensing and 95.28% on finance in MLLM-CL, and achieves significant improvements in vision-centric and reasoning tasks in COIN, with 95.61% on ImageNet and 77.84% on Science QA. We further evaluate on the MLLM-CL domain benchmark, showing improvements across metrics including MFT, MFN, MAA, and BWT. That is the end of our presentation. Thank you for your attention.